We have already classified the FM generation techniques into two categories, direct and indirect. In this lecture, our focus is on the indirect approach, which is better known as the Armstrong method. So why this method so important? Because it was the first practical technique that made the wideband FM broadcasting possible. Developed in the 1930s by Edwin Howard Armstrong, often called the father of FM radio, this method solved the problems of noise that plagued earlier FM system and set foundation for the modern FM communication. The Armstrong method works in a clever step-by-step process. It begins by generating a narrowband FM signal using a crystal control oscillator and a phase modulator. Then, through frequency multiplication and mixing, this narrowband FM signal is expanded into a wideband FM signal with excellent frequency stability. Thanks to this innovation, FM broadcasting became practical, reliable, and far superior to the AM in terms of noise performance. Armstrong's invention of FM significantly reduced noise and interference compared to AM, revolutionizing radio broadcasting. The Armstrong method was the only practical way to generate stable wideband FM for decades before direct varactor and PLL methods became common. Even today, high-power broadcast stations sometimes rely on variants of this method for superior stability. Now let's dive into the Armstrong or indirect method of FM generation and see how it works in detail. At first, let's see the block diagram of the Armstrong method or indirect method of FM generation. First component of the block diagram is the narrowband angle modulator. It takes the modulating signal MT and a low frequency carrier signal CT generated by a crystal oscillator at the frequency FC, producing a narrowband FM or PM signal XT with very small deviation. This signal is given as the input to the frequency multiplier. This frequency multiplier XN receives the narrowband signal XT and uses a nonlinear device, for example a class C amplifier, to multiply both the carrier frequency and the deviation, producing a signal YT with increased frequency and deviation. This multiplied signal is given as an input to the mixer. The mixer combines the multiplied signal XCT with a local oscillator signal, producing sum and difference of the frequency YCT. This mixed signal is then given as an input to the bandpass filter. The bandpass filter selects the desired frequency while keeping the deviation unchanged, producing a filtered signal. This filter signal is given as an input to an additional frequency multiplier. This additional frequency multiplier scales the filtered signal's carrier frequency and deviation, producing the final wideband FM signal ZT with the required specification. Now let us examine each block of the Armstrong method in detail to understand how it functions. Step 1 is the narrowband angle modulator. The process of generating a wideband angle modulated signal begins with the creation of a narrowband angle modulated signal. This stage of narrowband angle modulator requires two essential inputs: the modulating signal or message signal MT. It is a low frequency baseband signal that contains the actual information to be transmitted in the form of voice, music, or data. The next signal is the carrier signal, which is a stable high frequency sinusoidal signal generated by a crystal oscillator. It is chosen because of its frequency stability. It is expressed as CT, which is equal to AC cos omega CT or 2 pi FCT, or AC is the carrier amplitude and omega C is equal to 2 pi FCT is the angular frequency of the carrier. The angle modulator combines these two inputs to produce a narrowband frequency modulated signal FM or phase modulated signal PM. Mathematical expression. The generalized expression of the output is xt is equal to AC cos omega CT plus phi t, where AC is the carrier amplitude, 2 pi FCT is again carrier angular frequency, and phi t is the phase deviation introduced by the modulation process. The form of phi t depends on whether the system is frequency modulation or phase modulation. For frequency modulation, phi t is equal to kf integration of m tau with respect to d tau, where kf is the frequency sensitivity constant having the units radian per second per unit input. For frequency modulation, this phi t is equal to kp mt, where kp is the phase sensitivity constant having the unit radian per unit input. Now let us understand this narrowband condition. The narrowband condition applies when the modulation index beta is very small and the beta is defined as del phi divided by fm, where del phi is the peak frequency deviation in hertz and fm is the modulating signal frequency also in hertz. For narrowband fm signal, we require beta very less than 1. So that this means that frequency deviation del f is much smaller than the modulating signal frequency fm. Since the phase deviation is directly related to the modulation index, we also have phi t very small than 1. This means that the frequency of the phase deviation is much smaller than the carrier frequency. Therefore, the signal produced is a narrowband frequency modulated signal or narrowband phase modulated signal. Step 2 is the frequency multiplier xn. Once the narrowband frequency modulated signal has been generated, the next step is to increase both the carrier frequency and the carrier deviation using a frequency multiplier stage. A frequency multiplier is a memoryless nonlinear device whose output is tuned to a harmonic of the input carrier frequency. Since the device is memoryless, it means that it contains no energy storage elements like capacitor inductors that introduce delay. The input-output relation of a such nonlinear device can be expressed as V output is equal to A1 ST plus A2 ST square up to an st to the power n. Here a1, a2, n up to an depends on the device operating point and n represents the highest order of non-linearity. Such a device is often referred to as the nth power law device. Practical implementation. In practice, a Class C amplifier is commonly used as frequency multiplier. Its output tank circuit is tuned to a specific harmonic n into Fc of the carrier, effectively creating an n multiplier. The Class C amplifier conducts with a narrow conduction angle about 100 to 200 degree, producing strong harmonics. Thus, higher multiplication factors are usually obtained by cascading 2 doublets and 3 triplets. The mathematical expression for this stage will be here input to the frequency multiplier is the narrowband FM signal, which is xt is equal to AC cos omega c t plus phi t, where AC is the carrier amplitude, omega c is the carrier angular frequency or 2 pi fc, phi t is the phase angle due to the modulation, and the instantaneous frequency Fit is equal to Fc plus k into Fm. If the signal passes through an n times frequency multiplier, the output becomes Yt is equal to AC cos n omega ct plus n phi t. This means that instantaneous frequency of the output is F prime t is equal to n into Fc plus k into n into Fm. Here both carrier frequency and the carrier frequency deviation are scaled by the factor n. As a result, even though the original signal was narrowband, the repeated multiplication stages increase the deviation until the condition for wideband frequency modulated signal YC is achieved, which is beta very greater than 1, where beta is the modulation index. Thus, the frequency multiplier serves a dual role. It raises the carrier frequency to a desired range and simultaneously expands the frequency deviation, effectively transforming the narrowband FM into a wideband FM. Next step of this step 3 is the mixer and the local oscillator. After passing through the frequency multiplier, the frequency modulated signal is now wideband. However, the carrier frequency at this stage is n into Fc, which may not match the actual frequency allocated for transmission. To shift the signal to desired frequency band, we use a mixer oscillator combination. A mixer is a nonlinear device that combines the two input signal. The first input is the wideband frequency modulated signal with the carrier frequency n into Fc, and the second input is the local oscillator signal with the frequency f0. The mixer produces two new frequency components, the sum frequency, which is nfc plus f0, and the difference frequency, which is nfc minus f0. We need to filter out our desired component. To obtain the required transmission frequency, the mixer output is passed through a bandpass filter. The bandpass filter is tuned to pass only the desired frequency, either the sum or the difference component, and the unwanted components are rejected. The mathematical form for this stage can be written as if the multiplier output is Yt is equal to AC cos n omega ct plus n phi t, and the local oscillator provides the signal V LOT is equal to cos omega naught t, then the mixer output contains the terms of the form YCT is equal to AC cos n omega c plus minus omega naught into t plus n phi t. After filtering, we select the required component. Let's say the difference of the frequency component, or z is equal to AC cos n omega c minus omega naught into t plus n phi t. Now this is very flexible for frequency assignment, since both n from the multiplier and the frequency f0, which is the local oscillator frequency, are adjustable. Now we can choose the values such that the output carrier matches the required transmission frequency. Thus, the output of the mixer oscillator stage is a wideband frequency modulated signal whose carrier frequency is precisely aligned with the desired transmission frequency. So, to wrap up the things, the Armstrong method, which is also known as the indirect method, is a systematic and reliable way to generate the wideband frequency modulated signals. It begins with the narrowband angle modulated signal. Through frequency multipliers, both the carrier frequency and deviation are expanded. A mixer with a local oscillator and a bandpass filter then shifts the signal to exact carrier frequency required for transmission. This method ensures the excellent frequency stability and high reliability, which is why it became one of the most important techniques in the history of FM broadcasting. In our next lecture, we'll look at the direct FM generation methods and compare them with the indirect methods approach to understand their relative strengths and applications. Thank you for watching. If you found this helpful, don't forget to like, share, and subscribe for more lectures on analog communication.